Hello again everyone, and welcome back to Double Award Physics. And in this episode we're going to have a look at conducting metals. Right, so what we have here is if you imagined yourself zoomed in on a metal, this is kind of what you would see in simplistic terms. What you would see is a lot of positive ions. Okay, so these are basically they're atoms, but they've had an electron removed from them. Okay, so they're overall plus charge. And like all objects in the universe, they are moving, they're vibrating. Okay, vibrating about a fixed position because they're locked together. Obviously, if they're all positively charged, they should fly apart, but they don't, and the reason they don't is because the whole place is filled with what's called a sea of delocalized electrons. Those of you who do GCSE chemistry and pay attention, this is a phrase that you use all the time. Okay, delocalized electrons. That means that they don't belong to any particular atom. They kind of just float about there. Right, now if we want to drive a current through this, if we want to make some electricity travel along this path, basically what we have to do is we have to make these electrons move. Okay, not an individual electron, but whole groups of them. Okay, this idea of charge. Now, generally speaking, when we talk about resistance, we talk about the amount of energy that's lost by a component, or amount of energy is given out. Sometimes that's intentional. For example, in heaters and in light bulbs and heaters are designed to be resistive. They create light by taking electrical energy out of the system. And sometimes it's not particularly desirable. In general wiring, you don't want a lot of resistance. You want the resistance to be as minimal as possible. Right, so imagine I have this guy here, and I want him to travel from this end to this end. Okay, instead of him being a single electron, let's imagine him as a group of charge. Okay, so he's carrying a certain number of volts, and as he goes through here, happy days, he's getting all the way through and out the other end. In which case, he wouldn't give up any energy at all. Unfortunately, that's not how it really happens. As this tries to travel through here, the vibration of this will either interfere with it, become attractive to it, bounce off it, collide with it. All sorts of options are available here that will slow this little electron down. Okay, so the poor little electron, as it's trying to make its way gently through here, is getting the bejesus beaten out of it basically by all these positive ions. Right? And eventually it will lose some energy. Okay? The amount of energy it loses is basically the voltage that is being used by this entire piece of wire. Okay, so factors that will affect this are that if you think about it, all that really matters is can this little electron get from here to the end of the wire with the least interruption from these ions. Okay, so things that are going to affect that. Number one will be how long the wire is. That makes sense. The longer the wire is, the more kind of positive ions it's going to have to get past, the more likely it is to get beaten up more, so it's going to lose more energy. Right. The second thing is the material of the wire. Different materials will have different numbers of ions and different charges of ions, different sizes of ions. Okay, so the material of the wire will absolutely change what the path for this little electron looks like. Okay, got that so far? Number three is the cross-sectional area, CSA, cross-sectional area, or in brackets, width of the wire. And you've got a big wide wire, and now, interestingly, you would think that a wider wire might actually increase the resistance, but it doesn't. Okay, and the reason that it doesn't is that my diagram is poor. Okay, the diagram gives you this idea that the positive ions are massive, and they're not. Remember from our work in nuclear stuff, the nucleus of the atom is very, very, very small. Most of the atom is empty space. So if I widen this wire, I create more paths in between these ions that I can get out through. Okay, so for the cross-sectional area, amazing, if you increase the width of a wire, you actually make life easier to flow through. It's a bit like a water pipe. If you increase the width of a water pipe, water flows through much more easily. Okay, and these are three things that you absolutely must know for an exam. You need to know that these actually affect the resistance of my wire, and you need to know how. Okay, so here are the three kind of effects how. So if we go for one, the length of the wire. If I increase the length of the wire, I will increase the resistance. Why? Simply because I am going to get involved in more collisions with more ions. Doubling the length of this wire, if I take this and I group it and I double the length of the wire, okay, out to there, then unfortunately when my little electron has to travel from here all the way across, it's got to get past 1, 2, 3, 4, 5, 6, 7, 8 full ranks of ions. Now that's not good. And that means that he's going to get absolutely pulverized. As opposed to here, he's only got to get through 4 ranks. So that's going to be half as difficult. Okay, so if I increase the length, I increase the resistance. Number 2, if I change the material, the resistance will change. Can't say any more than that. Okay, it depends on what I change the material to, depends on what the material looks like, but I'm pretty sure that the resistance will change. And finally, 3, if I increase the area, and by area I mean that if I look at the end of the wire, is it fat wire, thin wire, if I increase the area, that means I will decrease the resistance. 3 absolutely key things that you must know about the resistances of wires. Okay. Right, now experimentally, if I want to check and see how all this works, I'm generally speaking only interested in the length one. Okay, if I'm an examiner, I'm interested in could you do an experiment to change the length of the wire and show that it affects the resistance. And this is the experiment that you would do. You'd set up a power pack with an ammeter, a voltmeter. For safety reasons, I'd probably put in a variable resistor as well, just to keep the current low enough that you're not going to melt anything. So pop in a variable resistor there, grab that, shrink that down a bit, pop that up there. That's a regular resistor, of course, and a variable resistor, one that you have control of, that gets an arrow through it like that. Okay. Now, so what I do is I set this up. This thing here, this is a crocodile clip or a sliding contact or a point or some form of thing that you can move along. So we'll call this a crocodile clip. Okay, so what I do is I set up my voltmeter, connect to my crocodile clip. That's connected to the other end to my test wire, an ammeter, a voltmeter, variable resistor, power pack. Okay, now what I do here is I set my test wire out, as say maybe a meter's worth of test wire. I flick on the power pack, and I get myself a reading. And I'll take readings of the voltage and the current. So this is my table, and this is V, and this is my current I. And of course, we'd have units for those, V in volts, current in amps, and I'd also probably need a length column as well. Okay, otherwise, this doesn't make an awful lot of sense. So there's my length column. Okay. Little side note: in theory, you should always do your tables from left to right in terms of what you measure. So I will measure length first, then I'll measure the voltage, then I'll measure the current. Okay, so if I start off with a length of 100 centimeters. And of course I would have centimeters as my unit in my title. Then I'd take the voltage, say 4 volts or something like that there, and my oh dear, do not put units into tables. They should be at the top. And my current, let's say it's nice safe 0.25 amps. Okay. Then what I do is I take my sliding crocodile clip here and I move it down here. Make sure it all stays connected up, because all these wires will drag with you. And now actually I don't have a full length of wire. I've just got between these 2 points, because this bit out here is no longer connected to the circuit, so it doesn't count. No electricity travels that way because there's no complete way back around to the battery. Okay, so now I've got a result for say 90 centimeters. Okay. And the voltage it uses might be a little bit smaller. Let's say it's 3.6 volts maybe, and the current maybe changed a little bit. It's slightly shorter wire, slightly easier for it to get through. So let's say we get 0.27. Okay, but more current going through. And you keep going all the way through that, and once you've got a full list of V's and I's, you can plot all the resistances for this. Okay, or you could directly plot a graph of V against I. Okay, and we're going to have a look at that, and we're going to talk about graphs in our next episode. So join me then, and enjoy your small amount of free time now.